Hello everyone, I'm Naoto. I'm a student from Okayama University in Japan. Today, I'd like to talk about applying NMT for Japanese phonetic and prosodic information estimation for genuine Japanese end-to-end TTS. Recently, end-to-end TTS systems have been intensively studied, and English end-to-end TTS showed high potential for generating speech with high quality and naturalness. Our goal is developing genuine Japanese end-to-end TTS. However, for the construction of genuine Japanese end-to-end TTS systems, there are still several problems to be solved. The biggest obstacle is the front-end text processing, including phonetic and prosodic information estimation. It is more complicated than English grapheme to phoneme conversion, because this process includes polyphony disambiguation, word segmentation, and accent nucleus shift. In addition, the conventional PPI estimation takes expensive cost. At the current state, for the end-to-end Japanese TTS systems, inputs of TTS are estimated by conventional rule-based or statistical-based modules, or is given as a manually annotated source. So, why is Japanese text processing complicated? This section explains reasons. First, in Japanese writing system, there is no separation mark between words. For example, the Japanese sentence, "I like books," is written like this. So, word segmentation is harder. Second, Japanese writing system uses many types of character. English uses 52 types, including uppercase and lowercase. In Japanese, there are 50 types of kana and over 2,000 types of kanji for daily use. Third, kanji characters have multiple corresponding pronunciations that are determined by context. For example, the pronunciations of this word are karai and tsurai. Fourth, Japanese have complicated accent rules. Japanese is a pitch accent language, therefore it is important for Japanese TTS systems to assign an accent nucleus at appropriate positions. However, accent sandy, a phenomenon that accent nucleus may change depending on the context, makes task harder. Next, I am going to explain the conventional PPI estimation. The left figure shows an outline of PPI estimation in conventional TTS systems. The conventional PPI estimation is rule-based system and uses the dictionaries. This system searches each word of sentence from entries in the word dictionary. And this approach is expensive because the dictionaries need to maintain for new words. We propose to apply NMT model to PPI estimation. In our approach, NMT model handles input as character-based symbols, not word basis. This enables us to estimate PPIs even if input was an unknown word that comprise known characters. The types of token is more variable than word basis inputs. Therefore, we prepared a large amount of training data. We propose to apply two NMT architectures to PPI estimation. LSM model that has by LSM encoder and LSM decoder with attention, and transformer model. Input is Japanese sentence and output is PPI sequence. In these sequences, the box indicates the token, the minimum unit of the sequence, and the right table is a list of prosodic information symbols. Here is training condition for transformer. Preparing huge human-labeled training set is unfeasible. Therefore, the training set is generated by a conventional Japanese TTS system from over 5 million newspaper sentences. Although the Japanese TTS system generates PPIs 91% correctly, the generated pairs are regarded as ground truths in the training phase. In terms of the evaluation measure, we employ the concept of word accuracy. Accuracy is defined like this. Here, n is number of tokens in ground truth, s is number of substitutions, d is the number of deletions, and I is the number of insertions. We calculate 4 kinds of accuracy. First, PP accuracy concerns if phonetic and prosodic information are correct or not. Second, P accuracy concerns if only phonetic information is correct or not. Third, B accuracy is the accuracy of estimation in accent phrase boundaries and calculated for sentences whose all phonetic information is correctly estimated. Fourth, N accuracy is the accuracy of estimation in accent nuclear flags and calculated for sentences whose all phonetic information and accent phrase boundaries are correctly estimated. The accuracies are calculated comparing the estimated sentence and the ground truth using dynamic programming. We prepared test sets in 2 ways using the same sentences of 5,142 newspaper and blog sentences. First, the automatically generated test set that is generated by a conventional Japanese TTS system. It is the same way as training set. Using this automatically generated test set, we check whether the NMT models run the training set properly. Second, the manually annotated test set that is labeled by human. Using this manually annotated test set, we can know how good the NMT models that were trained with contaminated training data. Here is the experimental results. The upper table is accuracies evaluated by automatically generated set, and the lower is by manually annotated. In addition to results of LSTM and transformer, to know the performance of the conventional TTS system, the automatically generated set is evaluated using the manually annotated set. It is shown as conventional TTS system in the lower table. From the results of automatically generated test set, the NMT models showed high accuracy. This indicates that the NMT models learned the training set properly. From the results of manually annotated set, transformer shows high accuracy. Moreover, the performance difference between transformer and conventional Japanese TTS system is quite small, less than 0.5%. This indicates that transformer is successfully trained to estimate PPIs. In terms of the 2 proposed models, transformer outperformed LSTM in all kinds of accuracies for both the automatically generated set and the manually annotated set. Moreover, for both proposed models, the performance for the automatically generated set is slightly better than that for the manually annotated set. This is quite reasonable, because the NMT models are trained using the automatically generated dataset. For B accuracy and N accuracy, the performance degradations between test sets are quite larger than PP accuracy and P accuracy. These are because accent friends boundaries and accent nuclei are consistently generated by conventional TTS system, whereas there are variations in manually assignments. In terms of PP accuracy and P accuracy, both models show slightly better performance in P accuracy than in PP accuracy. This is reasonable because the types of tokens to be estimated are more in PP accuracy than in P accuracy. This slide shows the estimated example of kanji characters that have multiple corresponding pronunciations. In the case of kanji character gyo, the results indicated that NMT effectively uses context information extracted from characters around gyo. On the other hand, in the case of Japane, the proposed model failed to estimate appropriate phonetic information. This mainly because shortage of training data. We might need more data that contains Japane. This slide shows the estimated example of unknown words. For the confirmation of the advantages of our character basis modeling instead of word basis used in conventional system, the proposed model is evaluated by estimating phonetic information for unknown words that comprise non-kanji characters. Although kanji characters have multiple possible phonetic information, the proposed models work well for unknown words. We propose to apply NMT for estimating PPI from Japanese text. Our motivation is to develop genuine Japanese end-to-end TTS that does not require the word dictionaries. The models were trained using pairs of sentences, and there are PPIs that were generated by a conventional Japanese TTS system from 5 million sentences. In terms of evaluation on manually annotated dataset, 95% accuracy for PPI estimation. Judging from the results, NMT models are promising toward end-to-end Japanese TTS. That's it. Thank you for your kind attention.